In this video, we'll be talking about some of the challenges involved in photogrammetry and basically things that make it difficult for us to create our 3D reconstructions, or maybe the quality of our 3D reconstructions might be poor as a result. Now, one of the first ones is our image quality and quantity as well. In terms of computers, they say garbage in, garbage out. Well, we can do some things in improving our photographs, as we've looked at previously, but the better quality that we have in our photographs and the quantity we have of those photographs as an input to our photogrammetry approach, the better our outcome will be at the end. So we do want a large number of photographs, and we want a large overlap between those different photographs. If we've only got a 5 or 10% overlap or something, it's going to be really hard to do matching in that narrow region that they've actually got that overlap. So we want a large degree of overlap, and we don't want blurry images, and we don't want images where the contrast, for example, changes markedly between different images. Or maybe we've got some images which are really bright and some which are really dim, or some that have got a bright reflection in them. It's going to be really hard to match those images with some of our other images. One place I found this recently is I was using a robot, a USV, an unmanned surface vehicle, basically a little boat inside water tanks. And what I found is whenever we didn't decouple the noise very well from the vibration of the vessel as the propellers were turning, propelling it through the water to the camera, we needed a bit of rubber or something to dampen those vibrations. And whenever it was just coasting along without the motors going, we had beautiful, smooth video captured from our GoPro cameras. But as soon as we turned the motors on, we got this vibration, and that vibration would cause every second or third image to be quite blurry. And so that significantly affected the quality of the images that we were trying to stitch together. Another problem is occlusions, and occlusions are basically where we can see something from one image, but when we look from a different image, for example, we can't actually see it just because something else is in front of it. We might have, for example, these two blue pens. And if you're looking from this position here, you can see both of those pens. But as we turn and we take a picture that's more like this pen here is occluding this pen, and we can't actually see it anymore. That causes to say in this image, actually there's only one pen there. We can only see one pen. And that's something that we might need to deal with. I also mentioned our lighting conditions. And lighting conditions might be things like reflections. There might be significantly different lighting between our different images. For example, if the sun goes behind some heavy clouds or something like that. Maybe we've got long shadows, and those shadows keep changing through the course of our imaging. And those shadows, because we're trying to match different features, those shadows will appear as features, but they're appearing in different positions, depending on how long it's actually taken us to create all our image captures. Another area of big concern is moving objects. Now, if you're trying to capture something that's moving, well, all those features are moving about. A classic example of this is if we're trying to do a reasonably close-up view of a tree and the wind will be blowing. And even if the wind's just blowing a little bit, all those leaves or flowers and things are blowing all over the place, and it'll become very difficult for us to create accurate matches. We'll just get kind of a blur of where all these matches should have been because the leaves are all in different positions. Now, I've already mentioned that we can have various lens distortions and things like that. Cameras have what we call intrinsic and extrinsic parameters, and we want to make sure we know what they actually are so we can correct for any lens distortions that we might be having within our cameras. And also understanding, for example, at a certain distance, 10 pixels in our image will equal how many millimeters or meters on the ground or in real life. And data processing is a huge challenge within photogrammetry. A lot of these steps, particularly when we're matching images, when we're doing our point cloud representations, and when we're doing our dense mapping, are hugely CPU intensive. Now, some of the software will do this in the cloud, so they've got huge servers that are running these applications. But if we're running it on our own computer, we need to be wary of how much memory our computer has and how much processing resources we have, noting that some of these applications could tie up your computer for a few hours. So a few tips for when we're doing photogrammetry. One thing that we can do is we can go through our images and take out any blurred images or images where we've got significant changes or differences in our lighting conditions, for example. We also want to avoid objects that are pretty well featureless. They might be very smooth or very reflective or very flat, and it's just going to be hard to match features between these different images. We want to make sure we have good overlap. I don't know how many times I need to say that, between our different images, with a bit of a buffer there. So we want more overlap. The more overlap, the better. Now we can do a bit of time of day optimization here as well. We want to avoid times where we'll have long shadows or significantly moving shadows and things, for example, or a lot of glariness and things in our images. We want to make sure our images are all in focus, and we might need to change and tweak our software a bit to get a good balance between accuracy of 3D reconstruction along with processing time required.